Okay, so let's finally write down our summary for today's lecture. So the main thing that we learned today is the character of physical laws. In order for them to be compatible with the laws of special relativity, is that the left-hand side and the right-hand side of any physical law, where if, for example, F is ma or Maxwell's equations, the left-hand side must transform like a tensor of a particular rank, and the right-hand side should also transform as a tensor of the same rank. Okay, so if this is true, then the law will preserve the same form in all inertial reference frames. Okay, so law must preserve the same form in all inertial reference frames. And the only way to do that is if both sides of the law transform as tensors in exactly the same way. Okay. The second thing that we saw is, of course, Newton's laws have to be modified to be compatible with the principle of special relativity. And so you have to write down some generalized force in this way, and this force produces a change in what we call form momentum now. And what we saw is, in the absence, these have to be modified, and in the absence of external forces, it's not mass and momentum that are separately conserved, but some combination of a generalized mass energy, where for a single particle, the energy is related to its momentum and mass in this way. Okay, and it's this combination of total energy, px, py, and pz, that is conserved in the absence of any external forces to a system. Okay, so you get the idea of what is called form momentum conservation. And of course, what this also tells you is mass or rest mass is just a form of energy which is locked up with the particle. Okay, but it can be released in certain specific processes, as we saw with electrons and positrons, which can annihilate to photons. And finally, we saw that Maxwell's equations can be written in a way where the physical law has the nice property that the left-hand side transforms as tensors of a particular rank and the right-hand side transforms as tensors of a particular rank, provided we correctly identify the components of the electromagnetic field strength tensor. Okay, and Maxwell's equations are already compatible with special relativity. However, to make it apparent that they're compatible with special relativity, we just had to rearrange things and write them in the form of tensors. Okay, so writing it in the form of tensors makes the non-obvious fact that electric and magnetic fields must transform in a particular way from one reference frame to another. It makes it obvious how they transform. If you arrange them in a field strength tensor, the transformation of the field strength tensor is obvious. Okay, so this is just like writing the 4-velocity vector has an obvious transformation, but if I just write the components of velocity, those have a complicated transformation. Okay, so writing things as this tensor in this tensor notation is called making Lorentz transformations manifest or apparent. Okay, and once you do this, it becomes very clear when you write down physical laws whether they are consistent with Lorentz transformations or not. Okay, and finally we saw the Lorentz force law is also compatible with the principle of special relativity, provided we switch from identification of 3 momentum to the 3 components of 4 momentum, okay, which are these. Okay, so we need to make this switch, and when we do this, what we find is this. Okay, so the 3 components of this equation are exactly what you would expect for the Lorentz force law, provided we re-identify the components of the momentum 3 vector. And this also gives an interpretation to what the 0th component of the modified Newton's laws are. So the 0th component is related to the change in energy of the particle, which is experiencing the force. And this change in energy should just be, the change in energy per unit time should just be the delivered power.